Hello and welcome to the video solutions here for this Core Pure mock exam paper. So this here then is the second paper that we've produced as part of the Core Pure predicted papers for 2025, or in other words here, Set A Paper 2. Now, as I mentioned in the first predicted paper here, or in other words, Core Pure 1, these are just predictions. Please do use a variety of revision resources here for Core Pure. I don't want to waffle too much, right? But as always, this practice paper here closely follows the Pearson Edexcel specification for A-level further maths. Pearson Edexcel have no affiliation to this paper and are not responsible for any of the material featured in this paper. As always, you have 90 minutes to complete the paper. And for this video here then, or this paper, there are 9 questions in the paper. And as always then, the total number of marks for this paper is 75. Now, just a quick note here. I have changed the recording and the way that I'm presenting the video solutions here for this paper differently to paper 1. The reason that I've done this here is because I felt like paper 1 might have been a little bit trickier to follow along with, given that, I had to keep scrolling up and down rather than just having the question to the side here. So I've kind of gone back to our old format here where the question is completely visible on the page and we can kind of work through it together. But please do let me know in the comments whether you prefer this format here, the one that we've used in this video, or the format that we used in the previous video, right? So Core Pure 1. But other than that, right, I don't really have too much more to say here. So all I want to say then is good luck with your upcoming Core Pure exams. And as always, thank you so much for watching the video. So let's not waste any more time then, and let's just get started with question 1 here. So let's just get started here then with question 1. So as we can see then for question 1 here, what we've got is a woodwork company that sells 3 different tables to 3 different local retailers. The table below here, as we can see then, shows the quantity of each table ordered by each store and also their total order cost. So the question then says, using the information given in the table above here, form and solve a matrix equation to determine the price of each table. And we also need to show all of our working here. So this is question 1, right? We shouldn't really expect too much in terms of difficulty here. And basically all we need to do here then is just form a system of equations here that we want to solve, right? So we can form the system of equations here just by using this table, right? So along the top row here, I've got 12a plus 13b plus 6c must be equal to the total order cost, right? So my first equation here then is 12a. So we get 12a plus 13b. So plus 13b plus 6c is equal to 21,755. Like so. Now for my second equation here again, we just go along the middle row. So we get 20a, we get 16b, and then finally 9c here. And all of this then is equal to 31,900, like so. And then finally, for our final equation here then, for our system of equations here, I get 8a plus 3b plus 13c is equal to this. So 8a then plus 3b plus 13c is equal to 21,145 there. Okay. And this here then gives us our system of equations. What we want to do here then is solve this system of equations. Now we can easily do that then by using matrices here. So in matrix form then, let's just make a note here. So in matrix form, what we're going to obtain here, so we obtain, so I'm going to get a 3 by 3 matrix here. So I get 12, 13, 6 for the top row here. So 12, 13, and 6. Along the middle row here, we get 20, 16, and 9. So 20, 16, and 9 there. And then finally for the bottom row here, we get 8, 3, and 13. So 8, 3, and 13 there. So this here is my 3 by 3 matrix. And what I do now is I times this by the following matrices. So I've got A, B, and C, like so. And once I times these two matrices together here, right, this gives us the left-hand side here, or my system of equations. So on the right-hand side here, then, this must just be equal to the total order cost here, right? So 21,755, 31,900, and also 21,145 here. So if we just write that out in full then, I've got 21,755. I then get 31,900. And then finally here we get 21,145 there. Perfect. Okay. So if we want to find A, B, and C then, let's just write this underneath then. So A, B, and C here. And what we need to do here then is use inverse matrices. Now, if you've got a calculator, that's absolutely fine. Use your calculator here to find the inverse matrix. If your calculator cannot evaluate inverse matrices here, then unfortunately you're going to have to do this by hand. But what I would recommend here is in the short time before your upcoming exams here for Core Pure, just get a calculator that can do this, right? It's going to save you so much time, so much pain. I would definitely recommend getting a calculator that can evaluate inverse matrices here, okay? So we want ABC here, right? So what I'm going to do then is find the inverse of this matrix here. So if I do that and times through by the inverse of that matrix here on the left-hand side, they just cancel out, okay? And then on the right-hand side here, what I get then is the inverse of this matrix here times by this matrix here. So if I just write that down in full then, as we just said then, we get the inverse of this matrix here. So 12, 13, 6, 20, 16, and 9. And then finally 8, 3, and 13 here, okay? Like we said, we want the inverse of this matrix here, and we times it by this matrix here, okay? Now, obviously, just be careful that you get the order the right way around here. If you don't, then this isn't going to work out. So 21,755, 31,900, and then finally 21,145 there. Like so. And at this point here, then, all we now need to do is just put all of this here into our calculator. And what we find then is A, B, and C is equal to, so what I get here then is 640, I get 575, and then finally for C here, we get 1,100, okay? So A here is equal to 640, B is equal to 575, and then finally C here is equal to 1,100. Now, just be very, very careful here. Do make it clear then what the price of each individual table is. So to finish with here then, let me just do this in a different color. Let's just do it in red here. So therefore, the prices here, so the prices are, so table A is my top number here, £640. Table B then, what do we get here for table B? So table B is £575. And then finally to finish with here, we have table C. So table C then is, so what do we get for table C here? 1,100, okay? So 1,100 there. And there we have it then. So again, just to finish with here, please do make it clear what the individual prices are, okay? But there we have it then. Hopefully nice and straightforward there just to get us started. And that gives us the solution to question 1. So for question 2 then, as we can see here, right, this question is split into 2 different parts. So starting off with part A then, all we want to do here is explain why this integral here is an improper integral. And nice and easy then. And as you can see, right, it's just 1 mark. We shouldn't really be expecting too much work for this. All we need to say here then is because the upper limit is infinity. Because the upper limit is infinity. Okay. Something along those lines there gets us the first mark. Nice and easy for part A. Now for part B then, let's just do this underneath here. What we want to do here then is show that the integral of 1 over x times 3x plus 4 from 1 to infinity is equal to a quarter ln 7 over 3. So as soon as you see something like this integrand here, right, where we have 1 over x times 3x plus 4, the first thing that you should be thinking here is partial fractions, okay? So let's just begin here then by rewriting our integrand here as partial fractions. So 1 all over x times 3x plus 4. This here then is identical to a over x plus b all over 3x plus 4. Okay? Well, to obtain a and b here, what we can do then is write this as a times 3x plus 4 plus bx, and this here then is equal to 1. Okay? Now, if I just let x equal 0 here, so let x equal 0 here, then in that case, this b here would disappear, right? Because b times 0 is just 0, and then we can go on to solve for a here. So I get 3 times 0, which is 0, plus 4. So I get a times 4, giving us 4a is equal to 1. And in that case, then a here is a quarter. Okay? So we find the value of a. We now need to find the value of b. So to find b here, then, if we just let x be equal to, if I let x be equal to minus 4 over 3 here, like so, in that case, then what I get here is minus 4 over 3b is equal to 1. And in that case, then, solving for b here, b is equal to minus 3 over 4. Okay? So what I've got here, then, is the partial fraction decomposition for this algebraic fraction here. And what that means here, then, is we can now rewrite this integral here. Okay? So what I've now got, if we continue part b at the top here, so b continued. So for part b then, what I've now got here is the integral then from 1 to infinity for this here, but as we've just obtained then, this is the same then as 1 over 4x. So 1 over 4x plus b over 3x plus 4. Now b is minus 3 over 4. So I get minus then. So minus 3 here. So minus 3 over 4 times 3x plus 4. Okay, something like this here. And we're integrating then with respect to x. Okay. Now, what I'm going to do here then is just go term by term, right? And for now, don't worry about the limits, right? I know the upper limit here is infinity, but for now, just ignore that. So just go term by term here, and actually evaluating this integral here is pretty straightforward. So 1 over 4x, if I integrate this here, this is a quarter ln x, right? Because my derivative here is 4 times my numerator. So I get a quarter ln x. So a quarter ln x. And the same applies here then. So if you expand the bracket here in the denominator, so 4 times 3x is 12x. If I differentiate that, I get 12. And again, that's 4 times my numerator. So what I get here then for when I integrate this term here basically is minus 1 over 4. So minus 1 over 4 ln of 3x plus 4. Okay. Close my bracket here and our square brackets. And don't forget here then our limits of integration. So from 1 to infinity. Now at this stage here then, what I'm now going to do here is write this as a single logarithm, right? We have a difference of logs. So what I can do here then is write this as a single logarithm. And if we do that here then, nice and straightforward, what I get here is 1 over 4 ln of x over 3x plus 4. So ln of x all over 3x plus 4. Okay, so just using the basic laws of logarithms here. And again, don't forget your limits of integration, like so. Now, at this point here, what I now need to consider is the limit then. So let's just consider the limit here as x tends to infinity of this part here, so ln of x over 3x plus 4, okay? So ln of x over 3x plus 4. And basically here, what I need to consider then is what is the dominant behavior, okay? In a way, you can just think about this here. If you just replace x with infinity, kind of a little bit naughty, we shouldn't really be doing this, but we'll do it anyway. So kind of just replace x with infinity here. I get ln of x over, ln of infinity over 3 infinity plus 4. Now, the plus 4 is negligible. It won't really make a difference. So basically, I get ln of infinity over 3 infinity, and that would just cancel then to give us ln of 1 over 3, right? So this here is equal to ln of 1 over 3, okay? Like I said, a little bit naughty. We shouldn't really be thinking about limits and, you know, the concept of limits such as that in that way, but just to make our life a little bit easier, we'll plug it in like that. So to finish with here then, if we just go back to this line of working then, so a quarter ln of x over 3x plus 4 from 1 to infinity, we can now use this fact here, right? So the limit as x tends to infinity of ln of x over 3x plus 4 is equal to ln of 1 over 3. So what I've got here then, if I substitute in my upper limit and my lower limit here, is a quarter. We get a quarter ln of 1 over 3. So a quarter ln of 1 over 3. We now subtract the lower limit here. So this part was my upper limit of infinity. We now subtract then my lower limit of 1 here. So what I get here then is minus 1 over 4, or minus a quarter, ln, to substitute 1 into this expression here. So we get ln of 1 over 3 times 1 plus 4. So 3 plus 4, giving us a denominator of 7. So I get a quarter ln of 1 over 7. Okay. And as we can see, then we're getting pretty close to the required solution here. They've got 1 over 4 ln of 7 over 3. So let's just rewrite this here then as a single logarithm, and let's just see what happens. So I get 1 over 4. To get 1 over 4 ln, to get 1 over 3 all over 1 over 7. And 1 over 3 divided by 1 over 7 here, this is just the same then as 1 over 4 ln of 7 over 3. Okay, and notice here then, this is exactly what we wanted here. Okay, so as required there, and there we have it. So as required, giving us a solution to question 2. So moving on to the next question here then, question 3. And as we can see then, for the first part of question 3 here, we just want to show the following result. And as we can see, 2 marks for this, we shouldn't really be expecting too much work. Now for part A then, I am hoping that the method required here for part A is quite obvious, but just in case it's not, then all we need to do here is just rationalize the denominator. Okay, so let's just start then by writing down the left-hand side here. I've got 2 all over, so 2 all over the square root of r plus 2. Oh, so r plus 2 there, apologies, plus the square root of r, like so. And if we're going to rationalize the denominator here then, this will be equal to, so what I get here then is 2 times by the conjugate here, okay? So that's going to be the square root of r plus 2, so r plus 2 minus the square root of r, okay? And don't forget here then, we do the same with both the numerator and the denominator, okay? So on my denominator here then, I get the square root of r plus 2 plus the square root of r times by the square root of r plus 2 minus the square root of r, like so there, okay? Now at this point here then, let's just expand and simplify, okay? Now to begin with then, for my numerator here, I'm not going to expand this because what I'm expecting here is if I just get this right-hand side here, what I would expect then is at some point within the denominator here, I get a factor of 2, or I just get 2 here, and then we can just cancel, right? So I'll just leave that as it is for now. So 2 times by the square root then of r plus 2 minus the square root of r, like so. And this here then is all over. So hopefully you just notice here then that this is the difference of two squares. So the square root of r plus 2 times the square root of r plus 2, just simply r plus 2. So r plus 2 there. And then root r times minus root r, that just gives us minus r there. Okay. So what's going to happen here? I get r minus r, so they just cancel. I then get 2 times the square root of r plus 2 minus the square root of r all over 2. And at that point there, the 2's just cancel. So therefore then, in that case here, 2 all over the square root of r plus 2. So the square root of r plus 2 plus root r is equal to the square root of r plus 2 minus the square root of r, exactly as required. So root r plus 2 minus root r there, as required. Okay, so as required there. And there we have it then. That gives us the solution to part A of question 3. Now for the next part of this question here, we have part B. And for part B, then it says, hence determine the following summation. So the fact that it says hence determine would suggest that the answer from part A will probably be useful for answering part B, right? So for part B then, what do we have here? Well, just notice then, this here is exactly what we had in part A, right? So what I can do here then is just rewrite this summation using the result from part A. So I've got the summation here from r equals 1 to n of this here. So the square root of r plus 2 minus the square root of r. Okay. Now, part B then doesn't explicitly tell you which method to use here, but what you need to recognize then is for part B here, we do need to use the method of differences. Okay. So for the method of differences here, we start with the first few terms. We also want the last few terms, and hopefully we can see the pattern that will form. Okay. So if we let r equal 1 here, so let r equal 1, what do we get here then? So when r equals 1, I get the square root of 3 minus the square root of 1. To get root 3 minus root 1, don't bother writing this as 1 here, just keep it as root 1. So if I let r equal 2 here, so r equals 2, what do we get here then? So we get root 4. Again, don't bother writing this as 2, just keep it as root 4. Just makes things a little bit easier here. And I also get minus root 2. Okay, let's just keep going here. We'll do, say, the first 4 or 5 terms here, just so you can see the pattern that will form. So r equals 3. What do we get here then? I get root 5 minus root 3. If r equals 4, what do we get here then? To get root 6 minus root 4. And then if r equals 5 here, in that case then, what I get here is, so I get root 7 minus root 5, like so. And let's just skip ahead then. So now for the final 2 terms then, this would be r equals n minus 1, and also r equals n here, okay? So when r equals n minus 1 then, what do I get here? So n minus 1 plus 2, that just gives me n plus 1 here, right? Or the square root of n plus 1, I should say. It's the square root of n plus 1 minus the square root of n minus 1, okay? Like so. And then what do I get here? So when r equals n here, I get the square root of n plus 2. So the square root of n plus 2 here minus the square root of n. Okay? Like so there. So hopefully by inspection here, you can see what's going to happen. So if I just do this in a different color here, just so it's a little bit easier to see, this root 3 here would cancel with this minus root 3. This root 4 would cancel with this minus root 4 here. This root 5 would cancel with this minus root 5 here. The root 6 would cancel on the next row here, so on and so on. Okay? So at the beginning here, all I get left with then is minus root 1, minus root 2. I get these 2 terms here at the very beginning of our series. And then at the end of our series here, this will cancel and also this will cancel here. So what I get left with then is, and again, I'll just highlight these in a different color. I get left with this term here, this term here, this term here, and also this term here. Okay. So in that case then, what do we have here? So this summation, so the summation from r equals 1 to n of the square root of r plus 2 minus the square root of r is equal to, so put the positive terms first, right? So square root of n plus 2, so square root of n plus 2 plus the square root of n plus 1, like so. I've also got minus root 2, and also minus root 1. And minus root 1, right, that's just the same as minus 1 there. Okay? And this here then, this is our result for part B. So let me just highlight this in a different color. So I'll just put a box around this here, just to signify then that this here is our solution. Okay? This here then is the solution to part B. So that gives us the solution to part B. And now for the final part then of question 3 here, we have part C. So for part C then, it says hence show the following. So I've got this summation here, which again, is just the same as what we had in part B and result from part A, right? And this is from r equals 1 to 48. So this would suggest here then, again, given that it says hence as well, that the result or the answer from part B here will be useful for answering part C. So to get us started here then, what I've got here is the summation from r equals 1, so from r equals 1 to 48, okay? And it's for this here. So 2 all over the square root of r plus 2 plus the square root of r. Okay, apologies for my handwriting, by the way. It's never the prettiest, but hopefully you can just about read it. So in this case here, using our answer from part B then, all I actually need to do here is just substitute then 48 into this result here. Okay. So what that gives me here then is, I get the square root of 48 plus 2, so that's root 50. So what I'll do is I'll write it down in full here. So the square root of 48 plus 2, like so, plus the square root then of 48 plus 1. So 48 plus 1. I've got minus root 2 and also minus 1. We can't do anything with those two terms at the very end, right? So let's just simplify here and see what happens. So this here just gives us root 50. This here is the square root of 49, which is 7. So plus 7. This here, we can't do anything with, and same again here with the minus 1. So minus root 2 and also minus 1, like so. So I said we can't do anything with those. We can simplify those, but for now, I just want to keep it in, full working, just so you can see every step of my solution here. So for the next step then, root 50 here is just the same as, let's do that at the top then, root 50 is root 25, root 2, which is 5, root 2. So this here is 5 root 2 minus root 2, like so. 7 minus 1 is plus 6. And then finally here, what I get then is 5 root 2 minus root 2, giving us 4 root 2 plus 6. Okay. I've given it here as b root 2 plus a. It doesn't really matter too much, right? You just write it the other way around. So 6 plus 4 root 2 there. Okay. And in that case, then, if we just identify the values of a and b here, in that case, then a here is 6. So a equals 6, and b then is equal to 4. Okay. And there we have it then. So that gives us the solution there to question 3. So moving on to question 4 now, as we can see then here, we have a question on roots of polynomials. Now, typically, roots of polynomials is quite a straightforward topic, but this question here is a little bit more complicated. In fact, you could say it's a little bit more complex, right? A nice little pun there, given that we have these complex roots here. So let's just start off then with part A here. So for part A then, what do we need to do here? Well, we need to show then that alpha plus beta minus 4 is equal to 0, and also alpha beta minus 3 is equal to 0. So to get us started here, then we know that gamma is equal to 3 plus I. So gamma is equal to 3 plus I. And also delta here is the complex conjugate of gamma. So delta in that case then, that might be quite possibly the worst delta symbol ever, but we'll roll with it. So delta here is equal to 3 minus I. Okay? So what I know here then is the sum of our 4 roots here. So I've got alpha, beta, gamma, and delta. So alpha plus beta plus gamma plus delta. This here then is equal to minus b over a. Okay? So going back to the quartic here then. Well, I've got a is equal to 1. B is equal to minus 10. C, we don't know what that is. So put a question mark there. Same for D here. I don't know what that is. And then for E here, I'll just do that underneath. E is equal to 30. Okay. So I know what gamma is. I also know what delta is. So I've got alpha plus beta plus gamma, where gamma is 3 plus I. So 3 plus I plus delta, which is 3 minus I. Okay? And all of this here then is equal to minus b over a. So minus b over a then, what does that give us here? So I get minus 10 over 1. So that just gives me 10 here. Okay? So let's just simplify the left-hand side here. You might be able to see straight away that the plus I here and the minus I just cancel. So I get alpha plus beta. So alpha plus beta. 3 plus 3 is 6. So alpha plus beta plus 6 is equal to 10. And then finally here, alpha plus beta. 6 minus 10 is minus 4 is equal to 0. And just notice here then, this is exactly what we wanted for the first result anyway. So as required. Perfect. Now let's see if we can derive this result here as well. So for the second result here, alpha beta minus 3 is equal to 0. I'm going to make use then of the fact that alpha, beta, gamma, delta here is equal to E over A. Okay? Again, we know what gamma is, we know what delta is. So in that case then, we get alpha, beta, gamma here, which is 3 plus I, times by delta here, which is 3 minus I. Okay? For E over A then, well, E is 30, A is 1. So I just get 30 here on the right-hand side. Okay? Now for the left-hand side here, well, 3 plus I times 3 minus I, just notice here that this is the difference of 2 squares. So nice and straightforward then, I just get 3 times 3, which is 9. I times minus I is minus I squared. And minus I squared here is equal to 1. So 9 plus 1 is 10. So I get 10 alpha beta is equal to 30. And then just divide both sides by 10 here. So alpha beta is equal to 3. And then finally, just subtract 3 off both sides. So in that case then, alpha beta minus 3 is equal to 0 there. Okay? And again, just notice here, this is exactly what we wanted for the second result here. So as required, and there we have it. So that gives us the solution to part A. Now for part B then, this is where a good chunk of the work comes from for this question here. As we can see then, 5 marks, right? So let's just do this underneath here. So it says, hence find all the roots of the quartic equation and find the values of C and D here. So even if you couldn't answer part A, you can still go on to answer part B and obviously part C here. And the reason for that is because what they give you here in part A is the important part of this question, right? What I've got here is simultaneous equations. And what I want to do then is solve these simultaneous equations. So if I rearrange this equation here, making alpha the subject, what I get here then is alpha is 4 minus beta. Okay? What I'm now going to do here is substitute this into this equation here. We'll call that equation 2, right? So if I do that then, what do I get here? So I get beta times by 4 minus beta minus 3 is equal to 0. Okay? So let's just expand and simplify here where we can. So I get minus beta squared. So minus beta squared, beta times 4 is plus 4 beta. Okay, I've got the minus 3 here, and all of this is equal to 0. Okay, so let's just take everything over to the other side here, and that will just ensure that this beta squared term here is now positive. Okay, so if I do that here, then I get beta squared minus 4 beta plus 3 is equal to 0. Okay, and obviously what I want to do here then is just solve for beta, right? So the hope here is that this quadratic would factorize, and the good news here is that it does indeed factorize. So what I get here then is, so I get beta minus 1 times beta minus 3 here. Okay, and again, all of this is equal to 0. Now this gives me two solutions for beta here. We obtain that beta is equal to 1, and we also obtain here that beta is equal to 3. Now, we're not done here because what I also need then is alpha, right? Now, alpha then is equal to 4 minus beta. So when beta here is equal to 1, alpha then is 4 minus 1, giving us 3. And then when beta here is equal to 3, as you can see then, alpha is equal to 4 minus 3, giving us 1 there. So in that case then, what I can see here, what I can say here anyway, is that the roots are, so the roots are given as, so what do I get here then? So I get 1, 3, so 1, 3, and we've also got gamma and delta here from the beginning of the question. So 3 plus I, and also 3 minus I there. Okay. Now, there is still a little bit of work to kind of go here with part B, right? Because what I also need to do then is find the values of C and D here. So, where do we go from here? Well, if I want to find the value of C here, then we're going to use the fact that sigma alpha beta is equal to C over A. Okay. So, I don't know what C is, right? That's what we want to solve for. I do know the value of A. So A here is equal to 1. So I get C over 1 here, which is just C. And in that case then, what I get here, or sigma alpha beta, is that C is equal to, so I get alpha beta. So all I'm doing here, right, is just using this standard result, is equal to C over A, where A is 1, which is equal to C. Then we use this standard result here. So C is equal to alpha beta plus alpha gamma here plus alpha delta. So alpha delta. I then get beta gamma. So beta gamma plus beta delta. So beta delta. And then finally here, gamma delta. Okay. Now I know then the value here of alpha, beta, gamma, and delta, right? That's just these 4 roots. So alpha beta is 1 times 3. Alpha gamma is 1 times 3 plus I. Alpha delta is 1 times 3 minus I. Beta gamma, that is 3. That's 3 times 3 plus I. And then finally, we had gamma delta here, too many Greek letters. So gamma delta, that is 3 plus I times 3 minus I. Okay, so let's just expand here and simplify. So I get 3. This is 3 plus I. So plus 3 plus I. I then get 1 times 3. So again, I get 3 here. 1 times minus I is minus I. 3 times 3 is 9 plus 3i. And then finally here, I've got this double bracket, which again is just the difference of 2 squares. So I get 9 plus 1, giving us 10 there. Okay, I'm hoping I've not missed anything here. So I should get 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I am missing one. Which one am I missing here? So alpha, beta, alpha, gamma, alpha, delta, beta, gamma. Yep, I'm missing beta, delta. There we go. I thought I was missing something. So 3 times 3 minus I as well. Apologies there. So plus that on. Hopefully my working does still make sense here. Or you can follow along anyway. So I also get 9. So plus 9 minus 3i there. Okay. And if we just simplify here then, this I will cancel with this minus I here. Same again with the 3i and the minus 3i. So if I just simplify here then, what do we get? So 3 plus 3 plus 3 is 9. Plus another 9 is 18. Plus another 9 here is 27. Plus the 10, what it gives us here is that C is equal to 37 there. Okay. Now, again, we're still not finished here because what I also need then is the value of D. And as we can kind of see here, right, we do have a full screen. So let me just quickly clear the screen and then we can have a go at finding the value of D. So as we can see, then we've now cleared the top half of the screen. So let's just quickly finish part B and part C here for question 4. So let's just do this at the top here. So part B continued then. Well, for part B then, we've just found the value of C here. So C is equal to 37. And we also need to just find the value of D here. So what I'm going to do here then is make use of the fact that sigma, alpha, beta, gamma is equal to minus D over A. Okay. So I know the value of A, right? A is equal to 1. So this here is equal to minus D. In that case, then minus D here is equal to alpha, beta, gamma, plus alpha, beta, delta, alpha, beta, delta, and then get alpha, gamma, delta, alpha, gamma, delta, and then finally here, I also get beta, so plus beta, gamma, delta. Okay. Again, I know the value here or the root here for each one. So I know alpha, beta, gamma, and delta, right? I've got 1, 3, 3 plus I, and 3 minus I. So minus D then is equal to alpha, beta, gamma. So alpha is 1, beta is 3, gamma is 3 plus I. So I get 3 times 3 plus I. Plus, so I get alpha, beta, delta. So again, that's 3. And in this case here, we times it by 3 minus I. I've got alpha, gamma, delta here. So alpha is 1. So I've got 1 times by 3 plus I times 3 minus I. So 3 plus I times 3 minus I there, like so. And then finally here, beta times gamma delta. That's just 3 lots of this, right? So 3 lots of 3 plus I times 3 minus I there. Okay. So minus D here is equal to, so let's just expand and simplify here. So 9 plus 3i, 9 plus 3i, 9 minus 3i, like so. This here is just the difference of 2 squares. So this here, as we established a little bit earlier on in the question, is just plus 10. And this here then is just 3 times this again, which is 10. So 3 times 10 is 30. Okay, let's just simplify the right-hand side here. That just cancels with that. Minus D then is equal to, so I get 9 plus 9, which is 18, plus 10 there is 28, plus 30 gives me 58. But just be careful here, right? This is minus D. We want the value of D. So in that case, then D is equal to minus 58. Okay. And there we have it. So that gives us the values of C and D and also the roots here for part B. And then finally, for the very last part of this question, part C, all we want to do here then is show these roots on as opposed to off here. So on, apologies for that, show these roots on an Argand diagram. So for part C here, it's time to crack out the art skills here. It doesn't have to be amazing, by the way, but just need to show these roots on an Argand diagram. So if I just sketch my axes here, this being the imaginary axis, I've also got my real axis here. Okay, something like this. As you can see, my art skills are absolutely shocking, but it doesn't matter too much. All I want to do here then is sketch these 4 roots. So should hopefully be nice and straightforward here. So for the first 2 roots then, our real roots, 1 and 3. Let's say that this here is 1. It's that root there. And also this root here is 3. Okay, so that's 1 and 3 there. And then for the final 2 roots here, 3 plus I and 3 minus I, well, 3 plus I, that would be 3 units along and up I units, or 1 unit on the imaginary axis here. Let's just say here. So going from the origin here, O, we'll say something like that. This here is 3 plus I. And then finally for the final root here, then 3 minus I. Well, again, I go 3 units along and I now go down 1 unit here on the imaginary axis. And let's just say then, that would be say somewhere here. That's 3 minus I there, like so. And again, going from the origin here, we get something like this. Okay, it's supposed to be from the origin. But you get what I mean here. So 3 minus I there. And that is our final root. So if I just do those in a different color just to make it clear then, this is 3 plus I, this is 1, this is 3, and this here is 3 minus I there. Okay, something like that. Again, it doesn't need to be perfect. You know, please don't think you're going to get graded on your art skills. Just something showing the 4 roots here then on an Argand diagram, such as this here, would get you the 2 marks there. And there we have it then. So that gives us the solution to part C and the solution to question 4. Now for the next question here, then we have question 5. So as we can see then for question 5 here, we're given the following differential equation where k is just a constant. So for the first part of this question, part A, all we want to do then is find the general solution to the differential equation when, and as we can see then we have 3 different situations here. So let's just start off then with A part 1. So for A part 1 here, this is when the absolute value of k here is strictly greater than 2. So when the absolute value of k is strictly greater than 2 here, what's going to happen then? Well, to begin with here, let's just start by stating the auxiliary equation for this second order differential equation. And as we can see here, right, this is a homogeneous differential equation. So my auxiliary equation here, is given as, so what do I get here? So I get m squared. We get m squared plus 2km. So plus 2km plus 4 is equal to 0. Okay. Now what we want to do here then is solve the auxiliary equation for m. So I can see here straight away that this will not factorize. So to solve this here then, what we need to do is use the quadratic formula. So m here then. So m here is equal to, so I get minus b, so that's minus 2k, plus or minus, so plus or minus the square root then. So what do we get here? So we get b squared, so that's 2k all squared, so that's 4k squared. So 4k squared minus them. So 4 times a, which is 1, times c, which is 4. So 4 times 1 times 4 is 16 there. Okay. And all of this here is over 2a, which is 2 times 1, which is 2. Okay. And if we just simplify this here, then what would we get? So I've got minus 2k over 2, so that is minus k there. So minus k there. Now for the square root then of 4k squared minus 16, what I can do here is factor out the 4. I get 4 lots of k squared minus 4. Square root of 4 is 2, so I get 2 lots of the square root of k squared minus 4. And obviously the 2's just cancel here. So what I get then is plus or minus. So plus or minus here, the square root then of k squared minus 4. Okay. Now, if the absolute value then of k here is strictly greater than 2, then my auxiliary equation here would have 2 real roots, right? So just pick a value here. For example, k equals 3. I get 9 squared minus 4, right? Again, we have 2 real roots here. So let's just make a note then. So if k, or the absolute value of k anyway, is strictly greater than 2, then our auxiliary equation, so the auxiliary equation here has 2 real roots. Okay. And in that case, then the general solution here, hopefully nice and straightforward, is y is equal to, so I get a, e. So what I'm going to get here then is one of these as the positive solution. So ae to the power then of minus k plus the square root of k squared minus 4, like so, times by x here. And then we also get plus be. So be, it's nearly to the same power, right? We now want the negative solution here. So be to the power then of, so we get minus k minus the square root then of, so we get k squared minus 4 times by x here. Okay. And there we have it then. So that is the general solution when the absolute value of k is strictly greater than 2. Now for the second situation here then, this is part 2. This is when the absolute value of k is strictly less than 2. So for part 2 then, let's just continue underneath here. So if the absolute value of k is strictly less than 2, then what would happen in this situation here? Well, if you're not too sure, just substitute a value of k strictly less than 2 into the auxiliary equation here. And what you'd find then is our auxiliary equation here has 2 complex conjugate roots. So we just make a note here. The auxiliary equation has 2. So it has 2 complex conjugate roots. Okay. And these would be of the form then. So these will be of the form then minus k plus or minus I times by the square root then of 4 minus k squared. Okay. And in that case then, my general solution here, again, this is for y here. So y is equal to, so we get e to the minus kx. So e to the minus kx here times by, so I get a cos, inside my bracket here then, I get the square root of 4 minus k squared times by x. So the square root of 4 minus k squared times by x here, like so. And we also have plus b sine, so plus b sine, again, of the square root of 4 minus k squared times by x here. So b sine times by the square root here of 4 minus k squared times by x. Okay. Close that bracket and the full bracket there, like so. And there we have it then. So that is the general solution here for the second situation. And then finally, for the very last situation here, part 3, this is when the absolute value of k is equal to 2. So let's just do that over to the left-hand side here. So part 3 then, as we just said, if the absolute value of k here is equal to 2, then what would happen in this situation here? Well, in that case here, my square root then is just 0, right? And what I get left with here then is just one repeated root of minus k. So the auxiliary equation here, so my auxiliary equation here has one repeated root, which is minus k. Okay. And in that case, then my general solution here is of the form, it's y is equal to, so I get a plus bx. So a plus bx, and we times this by e to the minus kx here. Okay, like so. You could have put the e to the minus kx at the front. It doesn't really matter. Either way, this is what you should have got here. Okay, so there we have it then. That gives us the solution to part A. Now, as we can see then, right, we don't have too much room here to answer part B. So let's just quickly pause the video and clear the screen. So as we can see then, we've now cleared the screen here. So let's have a go then at answering part B. So for part B then, it says hence or otherwise when k equals 1, state the following. So for the first part here then, just want to state the general solution. Now, what I've included on the screen here then is the relevant part from part A to help us answer part B, right? Now, if k is equal to 1, then that is the middle situation here, right? The absolute value of k then is straight less than 2 here. So this is for part B. And in that case then, what I've got here is the general solution. So for the first part then, part 1, if I want the general solution when k equals 1, all I now need to do here is just substitute k equals 1 into the general solution, right? Nice and straightforward then. And in that case then, what I get here is y is equal to, so I get e to the minus 1 times x here. So just e to the minus x, right? We then times this by a cos. So a cos of, so what I've got here then is the square root of 4 minus 1 squared. So 4 minus 1 squared is just 4 minus 1. So I get the square root of 3 here. So I get a cos root 3 x, like so. And then for this part here, we get b sine again of root 3 times x. So b sine of root 3, again, times by x there, okay? And there we have it then. So nice and straightforward. That's all we need there for part 1 of part B. And now for the very last part then of this question here, so this is part B, part 2. It asks us what happens to y as x tends to infinity. So again, this is when k equals 1 here. So for part 2 then, so when k equals 1, what happens to y as x tends to infinity? So all we're going to do here is use the general solution here from the previous part to help us answer the second part here. Now, straight away then, what I can see here is when x tends to infinity. So when x tends to infinity here, this part on the outside, this e to the minus x then, this will tend to 0. So when x tends to infinity, e to the minus x tends to 0, right? If you want to test that, just pick an arbitrarily large value, substitute that into this function here, and you'll find then that it tends to 0. Now for this part here, inside the bracket then, well, the trig functions take values that are bounded. In other words, this is a bounded oscillation. So I just make a note here. So the trig functions, take values that are bounded. In other words, like we just said, right, this is just a bounded oscillation. And in that case, then, all that's going to happen here is as x tends to infinity, so as x tends to infinity here, in that case, then y here will just tend to 0 there. Okay. And there we have it then. So hopefully nothing too challenging there for the final part of question 5 here. But there we have it then. So that gives us the solution here to question 5. So if we now move on to the next question here, let's just have a go then at question 6. So for question 6 here, we're given this function here. So f of x is equal to 2 cos squared x minus 1 for x belonging to the set of real numbers. Now, for the first part of this question, part A, all we want to do then is find the exact mean value of f of x over this interval here. So for part A then, straight away, I can see a problem here. Now, my problem then is if I want to find the exact mean value of f of x over this interval here, then at some point we need to integrate f of x, right? And integrating 2 cos squared x minus 1 is not going to be pretty. So how do we get around this here? Well, to begin with then, let's just start by writing down f of x here. So f of x then is equal to, so it's just this here, right? So 2 cos squared x minus 1. Okay? Now this here should look familiar because from A-level maths then, 2 cos squared x minus 1 is identical to cos 2x. Okay? Now just be slightly careful here then, because when we're dealing with hyperbolic functions, right, we do need to use Osborne's rule here. Now, Osborne's rule in this case here does not change this identity for its, respective hyperbolic equivalent. So this here then, 2 cos squared x minus 1 is identical to cos 2x. And as you can see then, integrating this here, so integrating f of x when f of x is cos 2x, is much, much easier than this here. So let's just start then by finding the integral here of cos 2x from 0, so we're integrating here over this interval, so from 0 to ln 2, and we're integrating here then with respect to x, right? So nice and straightforward here. This is simply, so what do I get here then? So this is simply a half sine 2x. So a half sine 2x there, like so. And of course, don't forget our limits of integration here. So from 0 to ln 2 there. Okay? Now, at this point here, I just think it's easier to work with sine and any other hyperbolic function in its respective exponential definition. So what I've got here then is a half times by, so this here then is the same as e to the 2x minus e to the minus 2x all over 2 from 0, so from 0 to ln 2. And again, just to make life a little bit easier here, let's just factor out then this denominator of 2, or in other words, this factor of a half then. So on the outside here then, I've got a half times a half, which is 1 over 4. And then inside the bracket here, we simply get e to the 2x minus e to the minus 2x. So e to the 2x minus e to the minus 2x there. Okay? And again, this is from 0 to ln 2. So at this point here then, we're pretty close to, getting to the mean value, right? So let's just quickly finish evaluating f of x here. So what I get then is 1 over 4 times by, so e to the 2x then, so x here is ln 2, so that's e, I'll put this in a bracket here, so e to the 2 ln 2 minus e to the minus 2 ln 2, like so. That there is my upper limit, and then we subtract here the lower limit. Now, the lower limit then, this would be e to the 0 minus e to the 0, so 1 minus 1, just giving us 0 there. Okay, like so. So let's just keep going here then. We're getting pretty close to the solution. So 1 over 4 times by this here. So e to the 2 ln 2, that is e to the ln 4, which is just 4, right? Let's get 1 over 4 times by 4. This here then is minus e to the power then of ln 2 to the minus 2, which is just 1 over 4. I get 4 minus 1 over 4, like so. So 4 minus 1 over 4, that is 16 over 4 minus 1 over 4, that is 15 over 4. So I've got 1 over 4 times 15 over 4. And this here then is just 15 over 16. Okay? But just be careful here, right? This is not our solution because I don't just want the, the integral here of f of x with respect to x from 0 to ln 2. I actually want the exact mean value. So let's just finish this off over here then. So for the mean value here, don't forget then that the mean value here is equal to 1 all over, it's b minus a, times by the integral then, so times by the integral here of f of x with respect to x from, in this case, a to b. Okay? So just using this here then, so this here is the integral of f of x with respect to x from a to b. So in that case then, f bar here, mean value of f of x over this interval here is equal to, so it's 1 all over b minus a, so 1 all over, so that would be ln 2 minus 0, which is just ln 2, right? So 1 over ln 2 times by the integral then of f of x with respect to x from a to b, which as we've just evaluated here then is 15 over 16. Okay, so 1 over ln 2 times 15 over 16. And in that case here then, this just simplifies to give us 15 all over 16 ln 2 there. Okay, and there we have it then. So that is the solution there to part A. And now for the final part of this question here, then part B just says, hence find the exact mean value of f of x plus e to the x over the same interval. Now for part B then, we've done a lot of the work for this, right? Because we already know the exact mean value of f of x here. That's 15 over 16 ln 2. So all I now need to do here then is find the exact mean value of e to the x over this interval here, and then just add those together. So the mean value then, so mean value of, that's e to the x over this interval here, that's 0 to ln 2, that is equal to, so again, this is going to be 1 over ln 2, so 1 over ln 2 times by the integral then of f of x here, where f of x is e to the x. Oops, that's supposed to be an x there. E to the x with respect to x from 0 to ln 2. Okay. Apparently my pen keeps cutting off. I don't know why it doesn't want to work, but there we go. Let's just keep going before it completely dies. So this integral here should be nice and straightforward. Then if you integrate e to the x, you simply get e to the x, right? So what I've got here then is 1 over ln 2 times by, again, like we just said, right, we get e to the x here, so e to the x, and don't forget your limits of integration here from 0 to ln 2. Okay, so what do I get here? So what is this going to give me here? So I'm going to get e, well, in fact, let me write the 1 over ln 2 on the outside here. So 1 over ln 2 times by, so outside here, oh, well, inside I should say, I'm going to get e to ln 2, so e to ln 2, minus then my lower limit here of 0, so minus e to the 0. Okay? Well, e to ln 2, that is just 2, so I get 2 minus 1 here because e to the 0 is just 1, so I get 1 over ln 2 times by 2 minus 1, which is just 1. So in that case then, the mean value of e to the x over this interval here is simply 1 over ln 2. And in that case then, like we just said before, the exact mean value of f of x plus e to the x over this interval here is simply then the sum of the mean value of f of x plus the mean value of e to the x over this interval here. So therefore, the mean value, so the mean value here of f of x plus e to the x is, so like we just said then, let's just add this here and this here together. So I get 15 over 16 ln 2 plus 1 over ln 2. So what do I need to do here? Let's just times this here by 16 then to get this over a common denominator. So 15 over 16 ln 2 plus 16 over 16 ln 2. And just add your numerators together here, then we get 31 over 16 ln 2 there. Bosh. That's some nice maths there, right? Not the prettiest solution, I don't think, but there we go. It's in exact form, so that's all the question asks for. And that's absolutely fine there. So there we have it then. This here is the solution to part A, and this here then is the solution to part B, and that gives us the solution to question 6. So moving on to the next question here then, where we have question 7. Now, as we can see for question 7 here, we simply have a proof by induction. Now, proof by induction is normally pretty standard. It's either a divisibility result, a matrix result, or a series result. However, and you've probably noticed it already, this question here looks a little bit different, because what I've actually got here then is a proof by induction for a recurrence relation. Now, to date, this hasn't popped up on any Core Pure exams, but this is something that could pop up on your Core Pure exam. So for this question here, I just want to quickly run through an example of a proof by induction for a recurrence relation. The worst case scenario here is that it doesn't pop up on your Core Pure exam. In that case, I've kind of wasted maybe 10 minutes of your life. If that's the case, sorry. If it does pop up, then that's great, right? You know how to run through an example such as this one here, okay? Now, it is a proof by induction, so the method and the steps here are all the same. So we start with the base case here. So we let n equal 1. So if we let n equal 1 here, well, u1 is equal to 8. So u1 is equal to 8. And un here, that's u1 as well, is equal to 4 to the 1 plus 3 lots of 1 plus 1. So I get 4 plus 3 plus 1, which is also 8 here. And in that case then, it's true for n equals 1. So true for n equals 1 there. Okay? Nice and straightforward. Now for the next step here, this would be our assumption. So I'm going to assume here that this is true for, so assume true for n equals k. Okay? So if we assume that this is true for n equals k, in that case then, uk here, so uk here is equal to 4 to the k. So 4 to the k plus 3k plus 1. Okay? Now, for a moment here, let's just think about what we actually want here at the very end of this proof by induction. So what we want here then is to replace n with k plus 1. So k plus 1 here is equal to, so I should get 4 to the k plus 1. So 4 to the k plus 1 plus 3 lots of k plus 1 plus 1. Okay, this here then, this is what we want. Okay, so let's just kind of highlight this here in this bubble. So going back to what we've got here then for our recurrence relation, if n is equal to k, then u of k plus 1 here, so u of k plus 1 here is equal to get 4uk minus 9k. So 4uk minus 9k. Okay? And because we assume then that this is true for n equals k, I can just replace uk here with this here. So u of k plus 1 is equal to 4 lots of this here. So 4 lots of uk, that's 4 lots of 4 to the k plus 3k plus 1 minus 9k. Okay, so let's just expand this out here. So what do we get then? So 4 times 4 to the k is 4 to the k plus 1. 4 times 3k is plus 12k. And then 4 times 1 is plus 4. Okay? And then finally here, don't forget the minus 9k at the very end. So let's just simplify here then. So what do we get if we simplify here? I've got 4 to the k plus 1. I've got 12k minus 9k, so that's plus 3k. I've also got the plus 4 as well. Now, at this point here, things are starting to look pretty good, right? I've got 4 to the k plus 1. That's what we want as well. So 4 to the k plus 1. So at this step here then, what I need to do is just rewrite this here ever so slightly. So what I can do then is write this as 4 to the k plus 1. So just leave that as it is. So 3k plus 4, I can split this up here then. So the plus 4, I can split it up as 3 plus 1. I've got here plus 3k plus 3 plus 1. Okay. And hopefully what you recognize here then is we can now factor a 3 out here. So I get 4 to the k plus 1 plus 3 lots of, so 3 lots of k plus 1 plus 1, like so. And at this point here then, if this is true for n equals k, then it's also true for n equals k plus 1, right? This is the whole point of mathematical induction. So to finish with then, let's just give our conclusion here. So therefore, if true, for n equals k, then it's also true, for n equals k plus 1. Okay, just notice here then, this result is exactly what we wanted here. Okay, and since this is true then for n equals 1, and since true for n equals 1, then in that case, it must be true for all positive integers, right? As we want to prove here. And since true for n equals 1, then it's true for all n belonging to the set of positive integers here. Okay, like so. And there we have it then. So as you can see, right, the actual proof by induction here is a little bit different, but the key point here is not to panic, right? If you get something like this, or a similar example here then, it kind of popped up a few years ago, was a proof by induction for an nth derivative here. If something like this does pop up, please don't panic, just work through it in the same method here as you would for any other proof by induction, okay? But there we have it then, so that gives the solution here to question 7. Moving on to the penultimate question here then, where we have question 8. So straight away then, question 8 might scare some of the pure mathematicians amongst us, right? As soon as we see this word here, variance, right? Scary stuff, but don't panic too much. It kind of uses the result from stats, but it isn't a statistics question. Okay, so no need to panic here. But what I'm told then is the variance here, var n of the first n natural numbers, is given as follows. So for the first part of this question here, then I want to show that var n is equal to the following. So what do I do here then? So like we said then, don't panic here, given that this question instantly looks like a stats question. Obviously, it's using a result from stats, but it isn't a stats question. This here then is a question on series, right? And that's what you need to recognize. So the sigma notation should kind of give that away. Just in case then, like I said, this here is a question on series. So let me just start then by writing down this result here. So var n is equal to, so it's 1 over n times by the summation here from r equals 1 to n of r squared minus then, this here is all inside a bracket, so 1 over n times by the summation here, again from r equals 1 to n of r all squared. Okay, so this question here then, or the first part of this question anyway, is just using some standard results, right? The summation here of r and the summation of r squared. Okay, so again, if we just use our standard results here, what do I get then? So this part here is 1 over n times by the standard result then. So this is the summation of r squared from r equals 1 to n. So that there is simply 1 over 6 n. It's 1 over 6 n here times by n plus 1 times by 2n plus 1. Okay, so that's this first summation dealt with. Then what I do here is I subtract then. So what I've got here is all inside a bracket. So I've got 1 over n times by the standard result here. So this is the summation of r from r equals 1 to n here. So that is simply a half n times by n plus 1. Okay, I've got a lot of brackets here. That looks a little bit excessive, but that is correct. And all of this here then is squared. Okay, so at this point here then, it's just a matter of simplifying, and hopefully we should be able to obtain this result here. So this n here would cancel there. So I've got 1 over 6. So 1 over 6 times by n plus 1 times 2n plus 1, like so. Again, this n here would cancel with this n here. To get minus then, to get minus here, I'll put this all inside a bracket, given that we're going to square the whole thing here. So I'm going to get, I'll do this over a denominator as well, just because I'm squaring both top and bottom here. So I get n plus 1 all squared. So n plus 1 all squared, and that's all over 2 squared. Okay. In fact, let me just kind of get rid of that squared here, just because I don't think that's very clear what I'm doing here. I'm squaring this full expression, right? But if I just simplify it, then we obtain this here, and we square the full result here. Okay. So again, let's just keep simplifying here. I get 1 over 6 times n plus 1 times 2n plus 1 minus them. So this is minus 1 over 4 times by n plus 1 all squared. N plus 1 all squared. Now what can I do here? Well, as we can see then, they've got 1 over 12 here. So what I'm going to do then is factor out 1 over 12 times n plus 1. So 1 over 12 times n plus 1 here, right? The other thing that I can actually factor out then is the n plus 1. I've got an n plus 1 here and an n plus 1 squared there. So I factor out then 1 over 12 times n plus 1. So what do I get then inside my bracket here? So if I factor out 1 over 12 then n plus 1 here, then this part must be 2 lots of 2n plus 1. So 2 lots of 2n plus 1, like so. And then for this part here, if I factored out 1 over 12 n plus 1, this must be simply minus 3 lots of n plus 1 here. So minus 3 lots of n plus 1, like so. Well, let's just expand and simplify inside this bracket here. So again, I get 1 over 12 on the outside times by n plus 1. And now if we simplify inside this big bracket here, then what do we get? So I get 4n plus 2. So 4n plus 2 minus 3n minus 3. Minus 3n minus 3. Obviously, you could have just kind of skipped a step ahead here. I'm trying to show all steps of my work in here. So if you simplify this here, what I get then is 1 over 12 times n plus 1. This here then simplifies to give us 4n minus 3n, which is just n. And then 2 minus 3 is minus 1. So I get 1 over 12 times n plus 1 times n minus 1. But just notice here then, this is the difference of 2 squares, right? So n plus 1 times n minus 1 is simply n squared minus 1 here. So that is equal to 1 over 12 times n squared minus 1, exactly as required. Okay. So there we have it then. That gives us the solution to part A. Now for the second part of this question here, then part B, it says, hence find the variance of the first 100 natural numbers here. So for part B then, nice and straightforward here. Even if you couldn't derive the result in part A, you can still go on to answer part B and part C because we have the result that we require, right? So all I need to do here then is just substitute n equals 100 into this result here. So nice and straightforward, right? So for 2 marks then, really, honestly, nice and easy. In that case then, n here is equal to 100. So therefore, the variance of the first 100 natural numbers here is equal to, so it's 1 over 12 times by 100 squared minus 1. Obviously, just put this here into your calculator. And if you do this correctly, then what you should find here is we get 833.25 there. Okay. Again, hopefully nice and straightforward there. And now for the final part then, part C here. Let's see if we can just about fit this on underneath then. It says find the smallest positive integer n such that the variance of the first n natural numbers exceeds 2000. So what I'm looking for here then is the variance of n to be strictly greater than 2000, right? That's what we want here. Now, the variance of n then, well, we know that the variance of n here is the following result, right? So what I've got here then is 1 over 12 times by n squared minus 1 is strictly greater than 2000. Okay? And all I need to do here then is just solve this quadratic inequality, right? So just times 3 by 12. So n squared minus 1 is strictly greater than 24,000. So 24,000. Add 1 to both sides. So n squared is strictly greater than 24,000 and 1. And then just take the square root here of both sides, right? And in that case, then n here must be strictly greater than 154.922, so on and so on. We'll just be very, very careful here, right? So what we're looking for then is the smallest positive integer, so integer n, such that the variance of the first n natural numbers exceeds 2000. So in that case then, so therefore the smallest integer, n, such that the variance then, such that var n here is strictly greater than 2000 is, so basically all I need to do here then is just round this up to the next integer. So in that case then, this is 155 there. Okay. And there we have it then. So that gives us the solution here to question 8. And then finally, to finish with here, we have the very last question, question 9. So what do we have here then for question 9? Well, to be honest, it looks more like a mechanics problem, right? As soon as we start talking about particles and moving with velocity, displacement, so on and so on, I instantly think it looks more like a mechanics problem, but it is still core pure. So let's just read the question here. So we have a particle P that's attached to one end of a light elastic spring. The other end of the spring is fixed to a point A on the smooth horizontal surface on which P is resting. The particle is held at rest with AP being equal to 1 meter and then released. So at time t seconds, the displacement of the particle from A is x meters, and the motion of the particle can be modeled by using this differential equation here. Oops, like so. Okay. So for the first part of this question here, then part A, hopefully nice and straightforward here just to get us started. So what do we want to do here? Well, all we want to do then is describe the motion of the particle. And as we can see then for 1 mark here, we shouldn't really be expecting too much work, right? So for part A then, what you need to recognize here, based on this differential equation here, is that the particle, let's just state this here, the particle is moving with simple harmonic motion. So simple harmonic motion there. Okay. And there we have it, right? It is only 1 mark. We don't need anything too fancy. That would be absolutely fine there. Okay. And there we have it then. So it gives us the solution here to part A. Now for the next part of the question here, we're given that x is equal to 0.4 and that the particle is at rest when t is equal to 0. So for part B then, what we want to do here is solve the differential equation to find x as a function of t. Right, so where do I begin here? Well, I've got the second order differential equation here, right? So x double dot plus 50x is equal to 0. So what I've actually got here is a second order homogeneous differential equation. So what I've got here then is my auxiliary equation. So my auxiliary equation here then would be, so what I get here then is m squared. So m squared, so this x double dot here, this is the second derivative of x with respect to time t plus 50x. That's m squared plus 50. Okay, and this here then is equal to 0. So just in case you're not too familiar with this notation here, you should be. We are studying A-level for maths and core pure, but just in case you're not, then this here, this is the second derivative of x then, and with respect to time t, and this would be plus 50x here. Okay, and this here then is equal to 0. So that gives us this auxiliary equation here, m squared plus 50 is equal to 0. What we now need to do here then is just solve for m. In that case then, just subtract 50 off both sides and solve for m, and hopefully nice and straightforward here. So m then is equal to get plus or minus, I root 50. Okay, now root 50 then, we can rewrite this, right? This is root 25 times root 2, and root 25 is 5. So what I get here then is plus or minus let's try again. I'm just about to write down the exact same solution, which doesn't make much sense. So plus or minus 5i, there we go, 5i root 2. Okay, that looks better. So in that case then, what I get here is that x is equal to, so we get a cos 5 root 2t, so 5 root 2t plus b sine, so plus b sine, again, 5 root 2t. So 5 root 2t there. Okay. Now, what I've got here then is these conditions, right? X equal to 0.4, and the particle is at rest when t is equal to 0. So what that's also telling us here then is x dot is equal to 0. Okay. So let's just make a note here then. So when t is equal to 0, x is equal to 0.4. Okay. So with that in mind then, what I can do here is substitute t equals 0 and x equals 0.4 into this here. So what I get here then is a cos of 0. So a cos 0 plus b sine of 0. So b sine of 0 is equal to 0.4. Okay. In that case then, b sine of 0 is just 0. Cos 0 is 1. So a times 1 is a. In that case then, a here is equal to 0.4. But we're not done here because we also want to find the value of b. So to obtain the value of b here, we also know that when t is equal to 0, the first derivative then, x dot here, is equal to 0. So x dot then is equal to 0. So what I now need to do here is obtain x dot. So x dot here then is just the derivative of x here with respect to time t. So let's just differentiate x here with respect to t. Should be nice and straightforward, right? Just basic A-level maths differentiation here. So if we do that then, what I get here is minus 5 root 2. So minus 5 root 2 a here. So minus 5 root 2 a sine 5 root 2 t, like so. So just be very, very careful here. It is easy to make just, a silly, tiny mistake rather than anything particularly challenging. So minus 5 root 2a sine 5 root 2t plus, and then get 5 root 2, so 5 root 2b cos 5 root 2t. Okay, like so. And we know then that when t is equal to 0, this here is also equal to 0. Okay. So using this condition here then, what do we get? So I get minus 5 root 2 a sine 5 root 2t. Obviously, I'm just going to times this here by 0. Times by 0 plus 5 root 2 b cos 5 root 2 times by 0 again. And this here then is equal to 0. And if we just solve here then, what I obtain is that b is equal to 0, right? Should hopefully be pretty trivial at this point. And at this point here then, we have now completed I'm going to say the question. Not the question just yet, but we have completed part B of this question here. Why is that the case then? Well, if we just go back to this equation here, in fact, let me do it in a different color. So we'll get rid of that. And let's just do this here in red. So this here, this is what's useful, right? And in that case then, because we've now found the value of A and also the value of B then, what I can now do here is express x as a function of t. So therefore in that case then, therefore x here is equal to, so b here is 0, right? So this term here just disappears because it's 0 times sine 5 root 2t. Well, anything times 0 is just 0. So that just disappears or just cancels. And what I get left with here then is a cos 5 root 2t. Now a then is 0.4. So simply here, I get 0.4 cos 5 root 2, 5 root 2 t there. Okay. And there we have it then. So this here, this is the solution to part B. Now for the next part of the question then, part C, we'll try attempt to fit this in this kind of like box here in the bottom left. We should hopefully have enough room, but we'll try anyway. So part C then, we want to find the period and amplitude of the motion. So let's just start then with the period of motion here. So for the period of motion here, like so, well, this is found then by solving 5 root 2 t is equal to 2 pi. Okay, so 5 root 2 t here is equal to 2 pi. Well, nice and straightforward then, right? Just divide both sides by 5 root 2 here. In that case then, t is equal to 2 pi all over 5 root 2, like so. What I can do here then is just rationalize, right? So 2 pi over 5 root 2 is just the same as, what would I get here? So I get 10 root 2 pi. So 10 root 2 pi all over 50. And I could just cancel down here, right? So 10 over 50 just gives me root 2 pi over 50. So root 2 pi, sorry, not over 50, over 5 there. There we go. Okay. And this here then is in seconds, right? We're solving for t here. And this is the period of motion. So we get root 2 pi over 5 seconds there. Okay. Now we're not done here because we also want the amplitude of the motion. So for the amplitude of the motion here, well, what I want to consider then is the largest displacement and when that occurs. So I'll just do this underneath here. It might be a little bit tight for room, but let's just see if we can make it here. So the largest displacement then, the largest displacement, this will occur, the largest displacement occurs when, so when does this happen here then? Well, that's when cos, so when cos of 5 root 2 t here is equal to 1, right? When this part here is equal to 1. So if this here then is equal to 1, in that case then x here is equal to 0.4 times 1, which is simply 0.4, right? And this here then gives me the amplitude of the motion. So therefore then the amplitude, so the amplitude here of the motion, this is simply 0.4 meters there. Okay. And there we have it then. So that gives the solution to part C there. So we have the period of motion here. That is root 2 pi over 5 seconds. And then for the amplitude of the motion here, that is 0.4 meters. And now, as we can see, then we have the very last part of this question here, part D. Unfortunately, we don't have quite enough room. So let me just quickly pause the video, clear the screen, and then let's just quickly answer part D to finish with here. So as we can see, then we've now cleared the screen here. So to finish with, let's just have a go then at part D here. So for part D then, what we want to do here then is find the maximum speed of the particle. So what I have included here is the relevant parts that you might find useful to help you answer part D, right? We've cleared the screen. I have included these few parts here as they're probably going to be quite useful to answer part D. Now for part D then, the velocity here, so the velocity here, so the velocity then is given by the first derivative here, right? X dot. So X dot then is equal to, so we know then that A is equal to 0.4 and B is equal to 0. So instantly then this term here just disappears because B is equal to 0. So I get minus 5 root 2 A sine 5 root 2 T. Now we also know the value of A, right? A is 0.4. So what I get here then is minus 0.4 times 5 root 2 here. So minus 0.4 times 5 root 2, like so. And then we times this here by sine 5 root 2 t. Okay. Well, minus 0.4 times 5 root 2 here, that just gives me minus 2 root 2. So x dot then is equal to minus 2 root 2 sine of 5 root 2 t. Okay. So the maximum velocity here, let's just make a note then. So the max velocity here, this must occur then when this bit here, so my trigonometric term, so sine 5 root 2 t, this part here must be equal to minus 1, right? So the max velocity occurs then when sine of 5 root 2 t is equal to minus 1. So if sine of 5 root 2 t is equal to minus 1, what I've got here then for the velocity is minus 2 root 2 times minus 1, in that case then giving us 2 root 2. So therefore the maximum speed, so the max speed of the particle this here then is equal to Vmax, which is simply 2 root 2, right? As we just mentioned before. So 2 root 2 there, okay? Don't forget units here as well, right? So this is the maximum speed. So my units then are meters per second. So 2 root 2 meters per second there, okay? And there we have it then. So that gives us the solution here to the very last part of this question, part D. And that gives us the solution here then to the very last question of this Core Pure mock exam paper, question 9, And that brings us to the end then of this video here. If you did make it all the way to the very end then, well done, right? I do appreciate that these videos are quite lengthy and can be quite tedious in nature. You know, it is a lot of maths and, you know, Core Pure, it's never easy, but hopefully you have found this paper and this revision video helpful in your exam prep and revision for your upcoming 2025 exams, right? So as always, thank you very much for watching and good luck in your upcoming Core Pure exams.